Hello everyone, welcome to this video. Uh, in this video, we will continue our discussion on multivariate random variables. This is based on the chapter 3 of uh, Demidenko's book. We have already covered a large number of topics under this chapter. We have discussed about joint and marginal probability density function and probability mass function, expected value, independence, and then conditional distribution, mixture distribution and Bayesian statistics, and random sum. Uh, in this lecture, we will start with covariance and correlation, and then we will continue to linear regression, distribution of order statistics, distribution of one-to-one transformations, uh, joint density upon transformations. Right. So I am not sure whether I will be able to cover all these topics today, but I will uh, discuss as many topics as possible to include in 3 videos, each approximately 1 hour of length. So, as the first part of today's lecture, I will first talk about covariance and correlation. Uh, remember, I want to first of all mention something important. Here we are going to discuss about the correlation and covariance between two random variables. And also later on we will talk about regression uh, between two variables. Here we are not discussing about the corresponding sample uh, quantities like sample correlation, sample covariance, or regression using a sample of data. That is not what we are discussing here. We are discussing about the correlation, covariance, regression related to random variables. Of course, there is a connection, but this is mainly about population quantities, right? So that you have to understand clearly the difference between this discussion here and the discussion usually done under correlation analysis and regression analysis, right? So first of all, we'll start with the definition of the covariance because we need covariance to talk about correlation. So the covariance between two random variables x and y uh, is defined as this. Right? So let x and y be random variables with means mu x and mu y respectively. So mu x is again the population mean, that is the expected value of x. Mu y is the expected value of y. So the covariance between x and y we denote as cov within bracket capital X comma capital Y is defined as the expected value of x minus mu x times y minus mu y. So it's just the product of two centered random variables. We consider first that and then take the expected value, right? So covariance between x and y is the expected value of the product of the two centered random variables. Covariance describes how x and y vary together about their means. you know about the variance, right? Variance described how the value of that particular random variable vary around its mean expected value. Right? Similarly, in this case, uh, covariance describes how X and Y vary together, right? Because we are always here talking about paired observations as a pair of random variables, how they vary together around their means. A positive covariance indicates a tendency for variable to move in the same direction, right? So that means in general, when the value of X increases, if the value of Y also increases with that, then we say there is a positive covariance. On the other hand, if the values of the two variables are going in opposite directions, in general, not always, in general, right? Then we say there is a negative covariance. If covariance between X and Y is equal to 0, the random variables are said to be uncorrelated. Right? So this is an important point here I want to emphasize. Covariance between X and Y is equal to 0 is interpreted as X and Y are uncorrelated. Sometimes this is wrongly interpreted as X, when covariance is equal to 0, it's wrongly interpreted as X and Y are independent. That is not correct. And we will look at some examples later to show that this is not correct. So the numerical size of the covariance depends on the measurement units. Right. It's very similar to the variance. You know, variance has squared units. Variance of some random variable X has the squared units of X. And similarly, in this case also, covariance has the units of X and Y because it involves X and Y both. Right. So X will be, say, in kilograms, Y will be in, say, centimeters. So then this product will be having kilogram centimeters, right? So measurements of X and Y will be involved. And it is therefore, it is difficult to interpret, right? If you say 10 kilogram centimeters, it's very difficult to interpret. So even though covariance actually gives you a measure of the variability of X and Y together around their mean point, right? There's a mean point. Mu X, mu Y is the mean point. But the value, it's very difficult to interpret because it depends on, first of all, the units of X and Y. And therefore, it's difficult to interpret. So therefore, we will look at a different measure later on uh, to measure the direction and the size of the relationship. But before that, we will look at some theoretical properties of this function called covariance. So covariance is a function of two random variables. So useful forms and elementary properties of the covariance. So one easy thing you can obtain from this definition, right? If you just expand this thing, you have X times Y and then mu X times Y, mu Y times X. Those are negative points and negative values, and then mu X times mu Y plus. So if you apply expected value to that, you can easily show that covariance XY is the same as expected value of X times Y minus mu X times mu Y. So that is an easier formula to apply when you are calculating or deriving the expression for the covariance. And if you consider the covariance between the same variable, x and x, for example, it is the same as the variance of x. For example, if you apply x and x here, so you'll have e to the power, exponential x square, then x times x square times mu x square in that case, because mu y will be the same as mu x. So we know that expected value of x square minus mu x square is the same as the variance. So from that, you can easily see that covariance of the same variable is variance. And there's a symmetry in covariance. Covariance between x and y is the same as the covariance between y and x. Right? It's coming from this definition. You can see that you can interchange x and y without changing and corresponding mu x. And you can see that from this one also, you can interchange x, y here and mu x, mu y here. It doesn't change. Right? So therefore, this is the symmetry. And then if you just add a constant to one variable, or you can, if you can add a constant to the other variable also. For example, in general, here it is shown as two parts, but you can consider simultaneously also covariance between x plus some constant and y is the same as covariance between x and y. So that means adding a constant to one variable doesn't change the covariance between x and y. And similarly, covariance of x and y plus alpha is the same as covariance between x and y. So in general, you can say covariance between x plus alpha and y plus beta will be the same as covariance of between x and y. Thus, adding a constant changes the mean but does not change the covariance. We know that when you add a constant to the variable, its mean changes, but covariance doesn't change. We can easily prove this result using either this expression or the original definition. But of course, when you multiply, if you multiply the variables by constants, you get this expression covariance between alpha x and beta y is the same as alpha beta times covariance xy. So those are very easy things to prove and easy to understand also practically. Consequently, changing the scale of either variables changes the covariance. Right? So if you divide by, for example, alpha and divide by beta, again, this will be divided by alpha and beta. Then we will look at some other properties. We can call them bilinearity. And also we look at the variance of a sum. Right? So covariance, say, between x and y plus z, y and z are random variables. You can expand using the usual usual mathematical expansion will be correct here also. So this will be equal to covariance between x and y plus covariance between x and z. Right? And similarly, the other way around here, you can consider this one because this will anyway be followed by the symmetry that we discussed. So there's nothing to discuss separately, even though I have given them separately here. If you consider the variance of x plus y, we can show that the variance of x plus y is equal to variance of x plus variance of y plus twice the covariance between x and y. How do we can prove it like this? You know that the variance is x plus y is one random variable. So variance of x plus y is the same as covariance between x plus y and x plus y. Right? Covariance between x plus y and x plus y. So if you expand that, right, like using this one, this expression here, then you will get this expression. So I am leaving it for you to verify. You'll get variance of x plus variance of y plus covariance between x and y plus covariance between y and x. That's what you will get. But that those two terms are the same. Therefore, you can say it's twice of that. If x and y are uncorrelated, of course, then this term is zero, and therefore you can say variance of x plus y is equal to variance of x plus variance of y. Right. So this is something you have to remember. If x and y are correlated, then variance of x plus y contains the covariance term. If x and y are uncorrelated, then in that case, variance of x plus y is equal to variance of x plus variance of y. Special case, if you apply here variance of x minus y, that is also variance of x plus variance of y. Right. So you can easily see that if you apply that to the definition, right? Even though you have minus here, you have plus. Remember that sometimes people just apply this thing, and then if you have a negative sign, some people put negative here. That is wrong. Right? You can easily prove this thing, even though we have plus sign here, minus sign here, this side will be the same. So in general, therefore, if you are adding, if you're considering the variance of n random variables which are uncorrelated, then it's equal to the sum of the variances of individual random variables. Okay, so now we are coming to the one thing important that we have to understand. If x and y are independent, then covariance between x and y is zero. But on the other hand, covariance between x and y equal to zero does not necessarily imply that the two random variables are independent. So recall that how do we define the independence? There are several ways to define independence. For example, you can define it using the mass function, joint mass function and joint density function, right? So for example, if the joint mass function or the joint density function, depending on whether the random variables are discrete or continuous, can be written as a product of the corresponding marginal mass functions or product of marginal density functions, then we say the two random variables are independent. That is one way to define the independence. Another way to define the independence is in terms of the expected value. If the expected value of x times y is equal to expected value of x times expected value of y, then we say x and y are independent. That definition comes from the previous definition, right? And there's another way to explain independence. That is, if the conditional distribution of one variable given the other variable, say the conditional distribution of x given y, is the same as the marginal distribution of x, that also implies x and y are independent. So now we can show that if the random variables are independent, then covariance is zero, but covariance zero doesn't necessarily imply the independence. So let's prove this. Independence implies zero covariance. It's very easy. If you look at the definition of the covariance, it is equal to this one. So because x and y are independent, right? If x and y are independent, then this term x minus mu x is independent of y minus mu y. Therefore, this product, expected value of the product, can be written as the product of expected values. And therefore, expected value of x minus mu x is zero. Expected value of y minus mu y is zero. Therefore, this will be zero. That is one way to look at it. Another way to look at it is to look at the second way of second expression of the covariance. For example, we have seen that covariance between x and y is the same as expected value of x times y minus expected value of x times expected value of y. But if x and y are independent, then this term will be expected value of x times expected value of y minus, we will get the same here. So therefore, this will give you 0. So that is the other way to look at it. So therefore, x and y are independent. It implies in this direction, covariance is 0. But the warning is that the converse is not true in general. Zero covariance rules out a linear association. It does not rule out any nonlinear association. We will understand this better a little later, right? We will see that the covariance actually measures only the linear association. So therefore, zero covariance means there is no linear association, but there can be a non-linear association. Right. Okay, I want to delete this part first now. Right. Okay, let's look at an example. Zero covariance, but not independent. Zero covariance with dependence. Suppose that there is a random variable x with mean 0, expected value of x to the power 3 is also 0, and suppose y is equal to x square. A particular example for this thing is standard normal. If you consider x to be a standard normal random variable, we know that expected value of x is 0. And in that case, expected for any normal distribution around 0, actually, not only standard, expected value of uh, uh, x cube is 0. And let's say y is equal to x square. So then the covariance between x and y is equal to covariance between x and x square. So that is equal to expected value of uh, the product of these two, that is expected value of x to the power 3 minus expected value of x times expected value of x square. So this term is 0 and this term is 0. Therefore, this is 0. So covariance. But you can see they are not independent very clearly because y is equal to x square. Right? So therefore, these are clearly dependent. Y and x are clearly dependent random variables. So that is an example. Therefore, uncorrelated does not necessarily mean independent. They are, in this case, dependent, but the covariance in this case is 0. Right. Now we are coming to the second measure of the association. As I mentioned, the covariance is usually difficult to interpret because its size depends on the size of our values of x and y, right? For example, the depends on the units. Uh, if x is measured in kilograms, y is measured in uh, say centimeters. So the covariance will be one value. If x is measured in grams, say pounds, and y is measured in um, inches, then for the same observations, but the units are different, the covariance will be a different value because remember that uh, covariance between alpha x and beta y is equal to alpha times beta times the covariance between x and y. Right. So alpha and beta will change depending on the units we use, and therefore the covariance will also change. Therefore, it will be difficult to interpret and compare the covariances. Say, suppose you want to compare covariance between X and Y and U and W, right? So if they are measured in two different units or separate completely different units, it will be very difficult to compare, right? We will be using covariance to get some idea about the variability of the pair of xy around the mean mu x mu y, but the value we get will change depending on what units we have used. So we can avoid this problem by considering a relative measure actually, so that the units will cancel out. There exists such a relative unit commonly used that is called correlation coefficient. Correlation coefficient, and in this case, we call it Pearson correlation coefficient. But again, I am warning here. When you say Pearson correlation coefficient, usually that comes into our mind is the sample Pearson correlation coefficient that we calculate using several pairs of XY values. That is the sample quantity. Here we are considering population correlation coefficient between X and Y according to the Pearson's definition, right? So suppose you have a random variable, sigma x greater than 0 means otherwise the only possible value is 0. If that will happen if only if x is a constant. So here when you say for sigma x greater than 0, we are in other words saying x is a random variable. And for sigma y greater than 0, right? Uh, the correlation coefficient is defined as this. On the other hand, this quantity cannot be defined if rho x or rho y or both were equal to 0. So therefore, mathematically, this condition is required for this quantity to be valid. So let's define rho to be the correlation between x and y. That is defined as the variance of covariance between x and y divided by the product of two standard deviations of x and y. So correlation can be considered as the covariance standardized by two standard deviations, right? Standardized or scaled by the two standard deviations. Now, covariance will have the unit of x and y as a product, right? For example, if x is in meters and y is in kilograms, though this will be meter kilogram. And sigma x will be in meters and sigma y will be in kilograms, so the units will cancel out, right? So that is a good thing. Rho will not be having a unit, therefore we call it a unit free quantity, unit free measure, right? Now, what are the other properties? It's unit free. That's an important and useful property. What are the other properties of the correlation? We can show that the correlation is always between -1 and +1, inclusive those two things. We can show that correlation coefficient, right, is between -1 and +1 by using the Cauchy-Schwarz inequality, right? Cauchy-Schwarz inequality will give us this inequality here. Covariance is less than or equal to the product, and therefore when you divide by that, here we are talking about absolute value because covariance can be negative also. So if you consider the absolute value always less than or equal to the product of these two quantities are always positive, right? So that this will imply that when you divide by these things, so absolute value of the correlation will be less than or equal to +1. So therefore, the correlation coefficient is between -1 and +1. But let me remind you, Cauchy-Schwarz inequality. We have already discussed this thing some time ago in our course. We looked at several inequalities in that lecture. The Cauchy-Schwarz inequality for two random variables u and v having finite second moments, that means expected value of squares, we have to assume they are finite. Then it states that expected value of uv, absolute value, less than or equal to the square root of expected value of u square and expected value of v square product. So this expression. So now let us consider a particular case. Let's say u is equal to x minus the expected value of x and v is equal to y minus the expected value of y. So if you apply that to this expression, then we get this expression, expected value of u times v, that is expected value of this times this, so that is equal to the covariance between x and y. And on this side, expected value of u square is the same as the variance of x. Okay? Expected value of the square of this term is the variance. And similarly, expected value of v square is the variance of y. So therefore, we can say covariance, right? Is absolute value is less than or equal to the square root of this. You can first get the covariance absolute value is less than this thing, right? Is equal to square root of, right? The Cauchy-Schwarz inequality. If you apply that directly to this, absolute value of covariance is less than or equal to this quantity. And then if you divide by that, you will see correlation is between -1 and +1. Right. Uh, we already have actually looked at the correlation term related to this. We saw that the correlation between alpha plus beta x and gamma plus delta x will be equal to the sign of product of beta and delta times the covariance. Now, using the same idea, same result, you can get this one for the correlation. So correlation between a linear transformation of x and another linear transformation of y will be the same as the correlation between x and y multiplied by the constants multiplications of x and y in the linear transformations. So sign will be important, right? Sign. Otherwise, the value alpha beta doesn't come. For the covariance, of course, value comes with the sign. But for the correlation, only the sign of this product will come because alpha and beta, beta and delta will cancel out with the term in the denominator. Right. So those things you can easily prove by using the definition. So therefore, I'm not going to prove them. I ask you to prove them as exercises. Right. So, but this is an important result to remember. Right. The correlation between two linear transformations of x and y is the same as the correlation between x and y with the sign of the coefficients of x and y in the linear transformations, the product of those. Right. Now, how do we interpret the value of this rho? We already know rho is going to be between -1 and +1. So it can be any decimal number. But depending on that, how do we usually interpret? Well, the correlation coefficient or coefficient rho measures the direction and strength of the linear association between x and y. So where did this word linear come? Up to now, we were not talking about any linear association. So here we say the coefficient rho measures the direction and strength of a linear association between x and y. Yeah, up to now, it is not clear to us why this word linear is important. But when we discuss the regression, I will show you how this word linear comes. Right? So for the moment, we will just accept this. Rho is a measure of the direction and the strength of a linear association between X and Y. If rho is positive, that indicates a positive linear association. If rho is negative, that indicates a negative linear association between what? Between the two random variables. Rho equal to 0 indicates no linear association. It also indicates the two random variables are uncorrelated. But remember, rho equal to 0 indicates there is no linear association. But there may be some other association which is non-linear, right? So students should not interpret rho equal to 0 as there is no association. That is a wrong. Right? If you say there is no association when rho is equal to 0, that is a wrong interpretation. There can be a perfect linear, non-linear association. There can be a perfect non-linear association, yet rho can be 0. Right? So rho equal to 0 implies there is no linear association. There is no correlation. They are uncorrelated. Uh, Rho becomes positive 1 or negative 1. That means absolute value of rho becomes 1 if and only if X and Y are exactly linearly related. Exactly. Right. So here in this case, when you say rho equal greater than 0 indicates a positive linear association, it does not necessarily mean all the pairs, possible pairs of XY are on a straight line. In this case, it does not mean that they are on a straight line. They can be close to a straight line, right? Around a straight line, right? Straight line with a positive slope in that case. In this case, rho less than 0 indicates the possible values of X and Y. Pairs of X and Y, if you consider them as points, they will be around a straight line with a negative slope. But rho equal to 1 indicates that those possible values of X and Y are exactly on a straight line. Right? If rho is equal to 1, positive 1, that they are on a straight line with a positive slope. If rho is equal to negative 1, that indicates XY points are on a straight line with a negative slope. So, rho will be equal to 0 if rho will be equal to 1, negative 1 or positive 1 if y minus mu y is equal to some constant times x minus mu x, or in general y is equal to something like alpha plus beta x. Right? They are on a straight line. So in this case, the sign of this theta here determines whether rho is equal to 1 or rho is equal to negative. In other words, in general, if you consider y is equal to alpha plus beta x, if beta is positive, then rho will be 1. If beta is negative, then rho will be negative 1. Right? If y is exactly equal to alpha plus beta x. If in addition x and y are independent, of course, we know that if x and y are independent, covariance between x and y is equal to 0. Therefore, rho, that is the correlation coefficient, will also be equal to 0. But the reverse implication requires additional assumptions, as in the covariance ratio. I stress that covariance equal to 0 does not imply independence necessarily. Similarly, correlation equal to 0 does not necessarily imply independence. It does hold for non-degenerate jointly normal pair and for a non-degenerate non-degenerate pair of bivariate random variables. Right. So this gives you an exceptional case where rho equal to 0 actually implies the independence. Right? In general, rho equal to 0 does not imply independence between two random variables. But for this, these are two examples, special examples where rho equal to 0 actually implies independence. One situation is a pair of two random variables which have a jointly a bivariate normal distribution. A non-degenerate means x and y are not constant. So right, that word is not that important here. We are talking about random variables. And similarly, if two random variables jointly have a bivariate Bernoulli distribution, in that case also, rho equal to 0 implies the random variables are independent. So we will now look at those two examples. Those are two particular cases. Zero correlation implies independence for Bernoulli random variables. Suppose the random pair x and y has a bivariate Bernoulli distribution, or the joint Bernoulli distribution with the following joint probability mass function. Suppose the probability that x equal to I and y equal to j, where I and j can be only 0 or 1, is equal to theta ij, right? Theta ij is equal to probability x equal to I and y equal to j, where I and j are either 0 or 1. So there are four possibilities: theta 0, 0, theta 0, 1, theta 1, 0, and theta 1, 1. So those probabilities we can show in a table like this, right? Theta 0, 0, theta. So this x taking value 0 or 1, y taking 0 or 1. So this is the probability that x equal to 0 and y equal to 0, theta 0, 0. It is the notation. And similarly the other ones. And then you know how to get the marginal probability mass function when you know the joint probability mass function. You just add the rows, then you get the marginal probability mass function of x. So the sum of these two we denote by theta 0 dot, because 0 is fixed here. The value changing is 0 and 1 second coefficient. So that is denoted by a dot in the mass function. That is a common notation. So that is actually theta 0, 0 plus theta 0, 1. And similarly, this one, when you add this row, you get theta 1 dot. So those are the two marginal probabilities, x equal to 1 and x equal to 0. X equal to 0 first and x equal to 1, this one. And similarly, to get the marginal probability mass function of y, you have to add the probabilities in the columns. So in this case, this probability y equal to 0 is denoted by theta dot 0. In this case, you can see that this 0 is fixed here. This one is the one changing. The subscript that is changing is represented by the dot here. And similarly, theta dot 1 is the probability y equal to 1. So suppose now correlation between x and y is equal to 0. Right. Then let's see whether that implies the independence. Right. So we'll assume that the correlation is equal to 0. And then we'll check whether the required conditions for independence are satisfied. Right. So in order to get an expression saying rho equal to 0, we have to first derive the expression for rho in this situation. Rho is the correlation coefficient. So that is the covariance divided by the product of two standard deviations. So therefore, we need to get expressions for the covariance between x and y and variances, and thereby get the standard deviations. In order to get the covariances, we can get the expected value of x times y and separately expected value of x and expected value of y. So we'll get these things first and then get the covariance and then get the correlation and then make it zero and get some expression. And then we'll see whether that expression implies the requirement for the independence. That's what we are going to do. So as shown in the table, probability mass function of x is given by this, right? Probability mass function of y is also given by this. So the probability mass function theta I dot, where I can be 0 and 1, and probability y equal to j is equal to theta dot j equal to 0 to 1. So we can write down it like that. So we see that x can take only two values, 0 and 1. So therefore, x actually is a Bernoulli random variable with the probability of success. That is probability that x equal to 1 being theta 1 dot, theta 1 dot. And similarly, y is a Bernoulli random variable with probability of success equal to theta dot 1. That is probability y equal to 1. Right. So therefore, we can either derive the expected value by first principles, or we can just use the things that we know about the Bernoulli distribution, right? For the Bernoulli distribution, we know that mean of the random variable is the same as the probability of success. So therefore, expected value of x should be equal to the probability of success theta 1 dot, and we can actually prove it like this. The 0 times the corresponding probability plus 1 times the corresponding probability. Then you get this same expression. And similarly, expected value of y is Bernoulli with probability of success equal to theta dot 1. So therefore, expected value of y should be equal to this. And you can prove it using the first principle definition of the expected value also like this. And then expected value of x times y, we can consider the four possibilities of x and y combinations. So 0 times 0 times theta 0, 0, 0 times 1 times theta 0, 1, and so on, right? Possible values, you just substitute for possible values of x and y, take the product and multiply by the corresponding probability, and then add them up, and then you get this answer, theta 1, 1. That is the expected value of x times y. And when because we know that x and y are Bernoulli, we can directly get the expression for the variance also. Variance of x is equal to the probability of success times 1 minus the probability of success. Similarly for the variance of y. So therefore, we can get the expression for the covariance. Covariance is equal to expected value of x times y, that is theta 1, 1, minus the expected value of x times expected value of y, that is the product of these two terms. So that is the covariance, right? Actually, in order to show what happens when the correlation is equal to 0, we don't have to derive directly the correlation. We can, if the correlation is 0, definitely covariance is also 0. So from this also, we can get the required condition for the covariance equal to 0. But I have anyway derived the correlation coefficient in this situation. Correlation coefficient in this situation is equal to the covariance divided by square root of the variance of x times the square root of the variance of y. So you get this expression. So now if the correlation is 0, that means this part is 0. This numerator is 0. So that means theta 1, 1 is equal to theta 1 dot minus theta dot 1. Right. So that means probability x equal to 1 and y equal to 1 is equal to probability x equal to 1 times the probability y equal to 1. So that is the expression that we get from this directly. But that alone does not show that x and y are independent. For x and y are to be independent, we should be able to write down uh, this expression for all possible values, right? If the probability x equal to I and y equal to j is equal to probability x equal to I times the probability y equal to j for all ij, right? Where I can be 0 and 1 and j can be 0 and 1. If this is satisfied for all ij, then only we can say x and y are independent, right? This alone, this expression alone will not imply that. But we can show that this expression, right? This expression, using this expression now, we can show that actually this, anyway, if you write down in general in terms of theta ij, this has to be theta ij has to be equal to theta ij has to be equal to theta I dot times theta dot j for all ij, right? So that is what we have to prove. Right? We have proved now here, assuming that rho equal to 0, it gives you the expression for I equal to 1 and j equal to 1 case. But we have to consider, show that this is true for all ij, right? So we can actually show that. For example, let me just take one and then I will leave them others for you to prove. I have proved them here. So let's consider theta 1, 0. Theta 1, 0 is equal, probability x equal to 1 and y equal to 0, right? So that is equal to theta 1 dot minus theta dot 1, 1, because some of this and this is equal to this one, right? This plus this equal to this one. Therefore, this is equal, this thing is equal to this one minus this one. But now we have an expression for theta 1, 1 coming from this one. When you substitute that expression, you will see that theta 1, 0 is equal to theta 1 dot times theta. This is actually, this term is theta dot 0, right? 1 minus theta dot 1 is equal to theta dot 0. So therefore, we can prove that theta 1, 0 is equal to theta 1 dot times theta dot 0. So that is one requirement here. And similarly, we can prove that theta 0, 1 is equal to theta 0 dot times theta dot 1. So that I have proved here. And similarly, theta 0, 0 should be equal to theta 0 dot times theta dot 0. That I have shown. Okay. So therefore, we see that x and y are independent. So therefore, this is a particular example where the covariance equal to 0 or correlation equal to 0 implies the independence between the two random variables. That is a particular case, a special case. And there is another special example where correlation equal to 0 or covariance equal to 0 implies independence. That is, if x and y are jointly bivariate normal. Right. So suppose x and y have jointly a bivariate normal distribution with means mu x and mu y, variances sigma x square and sigma y square, and correlation between x and y given by rho. So then the bivariate joint density function is written like this. This is the joint density function of a bivariate normal distribution. It contains mu x, mu y, sigma x, sigma y here, and also rho appearing here. And rho appearing here also. So now if x and y are uncorrelated, in other words, if rho is equal to 0, then this term will disappear. This product term will disappear. And this term will be just 1 here. So in that case, we get this joint density function. And that joint density function, we can easily see that that is actually the product of two individual normal distributions. Right? So this is a normal density, this is another normal density. This is a function of x only, this is a function of y only. Right? So therefore, we can see that fxy can be written as a product of two densities, one in X only, the other one is Y only. So that is showing that is one definition of independence. If you can factor the joint density into the product of two uh, marginal densities, then X and Y are independent. So here we have that situation. Therefore, we can say X and Y are independent. So this is an example we have already looked at some similar example. This is another one. A nonlinear relationship missed by correlation. Let's consider a random variable x, which has a standard normal distribution. And let's say y is equal to 1 minus x square. 1 minus x square. So x and y are completely related. Statistically, they are related. But let's look at the correlation or covariance. Let's look at the covariance. Covariance is equal to covariance between x and 1 minus x square. So that is equal to uh, covariance between x and 1 and minus covariance between x and x square. Right. But so that is equal to negative expected value of x to the power 3, right? We can directly apply the definition, right? So the definition for the covariance is equal to expected value of the product of the two terms minus the product of the expected value. So in that case, you can see this is equal to covariance of x times this quantity. So that is covariance of x uh, sorry, that is equal to the expected value of the product of these two. So let me write down. I made a small mistake there. Right. You can look at it in that way also in that case, but here it's easier to look at it here like this. Expected value of x times 1 minus x square minus expected value of x times expected value of 1 minus x square. Right. So this is expected value of x minus expected value of x to the power 3. And here we get minus expected value of x. And then expected value of 1 is just 1 minus expected value of x squared. Right. So when you simplify this, you get this term here. Right. So therefore, covariance is between x and y is equal to 0. So therefore, correlation will be 0. But we know uh, there is a perfect relationship. It's a perfect non-linear relationship. Right? So that relationship is not detected by uh, the Pearson's correlation coefficient. It is not detected by the Pearson's correlation coefficient. So that therefore we can see that that is one reason. Earlier I mentioned that the Pearson correlation coefficient measures the linear association, and we can later on we clearly see that it is measuring the linear association. Now we can, from this example, we can say that it is correlation coefficient is not measuring the nonlinear association. It is not measuring the nonlinear association, right? But in order to show that it is actually measuring the linear association, we have to wait until we come to regression. Okay, so that is the next topic. linear regression. In this section, again, we are not going to talk about what you usually call the regression analysis that we usually do when you get some data, pairs of data for two variables x and y, and then try to fit a model, a linear model like that. This is not what that one. Here we are going to consider uh, two random variables x and y, and then we are going to talk about something called linear regression uh, between the two random variables. So here we are going to consider actually a population phenomenon rather than a sample phenomenon. So that will be in the part two of this lecture.